only a single free moment that you can put anywhere on the structure and does the same thing. And if you have several couples, okay, you can just add the free moments, right? In 2D case, of course, just algebraically. If they're 3D, you just add them up, like just bunch of moments, okay? And then equivalent system, which was the most important conclusion resulting from the, introducing the concept of couples, and that meant what? If you have a force acting on a structure at any point, you can simply move that to any arbitrary point that you want from here to here, but the penalty that you pay as a result of this action by moving that force to a new location is you have to add the moment that this force generates about this new location. So if this distance is d, you just simply add a moment, which would be f times d, and then you get rid of this force. Or in other words, you can move a force from wherever it is acting to any other location by just simply moving that force, same orientation, to the new location, and add the moment of that force about that point at that point. That's the definition of equivalent system. So you have several forces, you can move all of them to a single point by just adding the moment that those forces create about that point and putting the resultant about those forces at that point. So that's what you want to do. Do an example that would be just that. Let's say you have a system like this, okay, point B. You have a force that is acting at 45 degrees from the line that is vertical to this beam. Another force, 90 Newton, at an angle of 20 degrees from this, and yet another force, okay, that is acting at 20 degrees from this vertical line. So what the problem is asking is that move all these forces to point B, or find an equivalent system at point B. That's what the problem is asking. So what do you need to do? In order to move all these forces to point B, what do? You just simply move every single force to that point. So I'm going to start with this one first, okay? So I will just take that force, move it to this location. In order for me to do that, what do I have to do? I need to add the moment that this force generates about point B and put it on the structure. How do I find the moment of this force about that point? I need to find the vertical distance from here to the direction, line of action of that force, and find that moment, put it here. Obviously, as you can see, it's not easy to find this vertical distance. So what do? We will remember Mr. Saint Viragnan, that whom you should always appreciate. What did he say? He said the action of a force is the sum of the actions of its resultants, of its components. So I will choose an XY coordinate system like this, instead of this. Okay, and resolve this force into its components. So the moment of this force about point B is the sum of the moment of these two components about point B, right? This is 216 sine of 55, and this is 216 cosine of 55 degrees. The nice thing about setting up the coordinate systems like that, as you can immediately see, is what? If you want to take the moment of these two forces, this force is passing through point B. That means the moment of that force about point B is what? 0. There is no vertical distance between this point and the line of action of this force, right? This is point B, this is that force, right? It's passing through that point. So there is no vertical distance from here to this line, because it resides on that line. So the vertical distance is 0. So anytime you take a moment of a force about the point, about that is along its line of action, that would be 0. So this doesn't generate a moment, only this one does. So the moment of that 216 Newton about point B would be simply 216 cosine of 55 degrees times the vertical distance, which is actually given, 0.45 meters, and this is 0.6 meters, times 0.45 degrees, 45 meters. And in what direction does it act? Counterclockwise, right? So that would be positive, right? So could you give me quickly how much that would be? Somebody could just do a quick calculation. Okay. Cosine 55 times 216 times 0.45.
55.75.
55. How about if I say 55.8 Newton meter? And this is
Wait, what did you get?
55.75.
That's what I got.
That's what, okay.
Oh, I might be in the room.
So, and it is in this direction. How about the moment that these two generate about that point? I would stop and look at them more closely, and I say, wait a minute, these are not forces. They're parallel forces, equal in magnitude, opposite in direction. That means they do not represent a force system. All they do is they generate a couple, right? So all I have to do, just find out what the couple moment that these two generate is and put it on the system, okay? So far what I have done then is I've moved that force to that location, and by doing so, I have also added a moment of 55.8 Newton meter there. So I've removed this, put it here, and this is what we have. Now I'm going to move these, that means put their couple moment at that point, or on the structure, because it's a free moment. Again, in order to find the moment that this couple generates, I need to know the vertical distance between the two. It's not easy. So again, what do I do? Who do I remember? Saint Verignon. Do not forget that famous saying. Resolve this into its components, and resolve this into its components. Some of the components, some of the action of the components is the same as the original force. So this is what? This is 90 cosine 20. This is 90 sine 20. This is 90 cosine 20. This is 90 sine 20. I need to find the moment of each of these components. These two obviously are a couple, but it happens that they're both acting along the same line. So they cancel each other. They don't generate any moment, they don't represent any force, right? It's only the couple resulting from these two which is going to act clockwise. And that moment of that 90 Newton couple would be then 90 cosine of 20 times the distance between the two, which is 0.6 plus 0.45, and it is acting clockwise or negative. So could you give me this number, 90 times cosine 20 times 1.05 meters? That would be
88.8.
88.8. 88.8 Newton meters clockwise. That is negative. So I will need to put that also in there, right? So I have 88.8 Newton meter. Or these two are added up, and therefore the action that results by moving this force and those couples to point B is what? Is going to be just a moment of 33.3 Newton meter and a force of 216 acting at that angle. So this system does exactly the same thing that the original system of these forces. These two are identical. They do exactly the same thing. We call this equivalent system to the original system. Okay, yes?
Wait, so we didn't account for the 90 sine 20 forces because they cancel out?
No, they cancel each other. These two cancel each other.
What about the sine force for the 216? Is it because it's on the same line?
Yeah, it doesn't generate any moment.
Okay.
Right, that one. So it's only this one. So when we move this to here, the moment that results from that movement is only due to the y component of that force. Okay. Any other questions? No? Yes.
So, though though the magnitude is canceled out of the forces, the moment stays.
What do you mean the magnitude cancels out?
Like the two forces cancel each other out.
You mean these two?
Yes.
Yes.
But the moment stays.
Yeah, because these two, right, they have no translational action, right? They cancel each other, and they don't generate any moment. Because again, there's no distance between them. They are, in a way, a special case of a couple, that the distance between the two forces is zero because they're along the same line. So they don't generate any moment, they don't generate any forces, so they're useless.
So there's
In other words, you're pulling a chair with a table 20 Newton, and somebody else pulling it with 20 Newton from the other end. The table is not gonna move. Yes?
Are we ever gonna get any ones where the point, like, that we're taking it from isn't on the line of action?
It can be, sure.
We-
In fact, let me do a problem like that. Sure. Good question. So I'm going to do, okay. All right, yeah, this is a good one. Well, it's a 3D. Okay, yeah, I believe I may have done or may not have done a problem like that, Well, let's do it. Okay? Let's do something like this. Okay? Let's say you have a system that looks like this. Let's say you have a structure like this, okay? And you want to move everything to point A, okay? You don't like all these cables or that are attached in all these different configurations, and you just want to basically replace all of these forces to a single point, and that single point is A, okay? So that's going to basically answer your question, that the point is not necessarily like here, is somewhere, right? Let's say this is the point A. Okay, so move all forces to point A. Or in other words, find an equivalent system of forces that is acting on this structure. So what do? You have to move every single force to point A. What does that mean? That means you find the resultant of all these forces at point A, right? As I always said, take advantage of Saint Verignon's theorem. Anytime you have any force which is not acting along X or Y direction, it's always the best to resolve the force into its components. Because the action of the sum of the action of the components, whatever this action is the same as the action of the original force. So I will always replace the force with its components. Okay? So let's do that. In this case, you have 20 cosine of 45. Cosine of 45 is square root of 2 over 2. So it would be 10, the square root 2, 10, the square root 2. The slope here is 345, so this would be 3/5 of 50, so it would be 30 Newton. This would be 40 Newton. This would be 80 cosine of 30, which is square root 3 over 2. So it would be 40 square root 3. This would be 80 sine 30, so it would be 40 Newton. So I've resolved for the forces to their components. So now I want to put all these forces here. That means I need to find summation of all forces acting along X, summation of all forces acting along Y, or the resultant of all of these, and put it there. What is the summation of all forces acting along X? You have 10 square root 2 plus 30 minus 40 square root 3. So while I'm doing the next one, somebody's going to give me this number. Okay? How about y? You have 10 square root 2 negative 40 negative 100 positive 40 is equal to this, and this cancel out. So what is this one?
Negative 25.1.
Yeah, I got that too.
25.1, thank you. And this one? That would be 10 times 14, so it would be out 86 maybe? Negative 86?
Negative
86.
85.8.
How much?
85.8.
Okay, negative, I would say 86. Oh, just round it up. So what that means, you will have a force with these components acting at that location. You have a force of 86.1 Newton and a force of 25.1 Newton. But now that you've moved all forces to that point, what does that mean? You will need to add the moment that every single force makes about that point A and add it to the structure. So I will start with this one, right? So what is the moment of this force about point A? Moment of that 20 Newton force about A is the moment of this 10 square root 2 about A plus moment of that component about A, right? Think about this, about point A or A. What direction that's going to be? Clockwise. So this is negative. How about this one? Counterclockwise. You know how to figure that out. Connect that point to this force and try to move that force. Imagine what direction that linkage is going to rotate. Okay? So that would be positive. So we already have the distance. You have 2 plus 10, 12. So the moment arm here is 12 times 10 square root 2. This is negative. For this one, the moment arm, which is the distance, vertical distance from here to this line, is 8. So you have plus 8 times 10 square root 2. So you have negative 4, right, times square root 2 Newton meter. That's for the first force, yes?
So just to clarify the difference of the moment of A, 10 square root 2, and then the second one, so the first one's in the x direction, the second one's in the y direction?
Right, you see,
Okay.
you're taking the moment of this force about that point, right?
Mhm.
That means you have a moment arm like this. It's gonna rotate in that direction. But how much is that moment? The magnitude of that moment is the vertical distance between this line of action and this point, which is this distance, which is 2 plus 6 plus 4, right? For this one, the vertical distance between this and this line, which is this, right? So this goes that way, this goes this way, okay? Yes?
Isn't it negative 40 root 2?
Negative 40, sorry, yes. Good point. Negative 40. Thank you. Okay. So that's for that. Same thing here. Moment of this 50 Newton force about point A would be the moment of that 30 Newton plus the moment of this 40 Newton about A. This one is going to rotate again clockwise. So this would be negative. This one also going to rotate clockwise. So this would be also negative. How much is the moment of this about this point A? The vertical distance from here to here, which is 10. So you have 10 times 30 negative. How about this one? This is the moment arm from here to this line. So that is 4. So it would be negative 4 times 40. Okay? So this would be 160 and 300, so 460 negative. Any questions? Okay, Newton meter. What else? Moment of this force. What would be the moment of that force about point A?
0.
0, because it is going through that point O. There is no vertical distance between that point and the line of action of the force, because the point resides along the line of action of the force. So that is 0. How about the moment of this guy? This component goes through that point, so it doesn't generate any moment. It's only this one. So therefore, I'm going to erase this to get that out of our way. So moment of 80 Newton about A would be moment of that 40 Newton about A, which is 0, plus the moment of that 40 square root 3 about A, and that rotates in that direction, so it would be positive, and the moment arm is 4. So this is simply 4 times 40 square root 3 would be 160 square root 3. Okay? So you just simply add all those moments. Okay? So moment of 20 Newton plus moment of 50 Newton plus a moment of 80 Newton force. So somebody can help me by adding these up. These two are negative. This one is positive.
239.5.
239, thank you.
Negative.
Negative?
Yeah.
Great. So that would be a moment like this. So the result of the action of moving all those forces to this point means you move the resultant here, and then you have to add a moment of 239.5 Newton meter at that point. So what it means, all these forces combined at those locations where they are applied do exactly the same thing to this structure as this system of forces on moments does. So you can replace all those cables, get rid of all of them by just putting a single force consisting of these two components, of course, here, and add a moment or a rotational spring that would exert a 239.5 Newton meter force. And as you can see, you have simplified the configuration of all these forces. But these two are exactly the same thing. Any questions?
Do you have to know the forces?
Which forces?
The 25.1 and 86.1?
Yeah, this is what we got. Basically what those forces are. How did we do that? We moved all of these forces to here. So these two forces represent the resultant of all those forces that we put there, or the components of the resultant. but what results from that action, meaning moving these forces to here, is that you need to put a moment that resolves from each force about this new location, add them all up, put it on the structure, which is what we did. Equivalent force, moving a force from the existing location to another location, you do what? You just move it there, but at the moment which resolves from that force about the new location. Yes?
Would you be able to use this method to find a moment about any point?
Any point.
On that?
In other words, if I had asked you to move all these forces to another location, you do exactly the same thing. If that's what your question is, yes? Yes.
Wait, so for the positive and negative symbols, that's based on the.
Clockwise or counterclockwise?
Is
You
it
remember?
clockwise negative?
Clockwise, we assume that it is negative. Counterclockwise, which is the same direction, you remember trigonometry? What direction you assume to be positive in trigonometry? Counterclockwise, right? Do you remember that wonderful unit circle in trigonometry?
Okay,
This
so,
was what? Cosine or sine?
okay.
This is cosine, this is sine, and we always measure angles this way, as positive.
Why is the 43 force positive?
Which one? This one?
Yeah, isn't it?
No, this is going to be positive.
Oh, really? Okay.
Yeah, counterclockwise. Because this force rotates about this point in time.
Oh, okay.
If
Okay.
you, this is the moment R, right? If you move that force, this
Okay.
linkage goes counterclockwise. Any other question? I don't think we have time to do another problem. I hope these problems were useful. We'll do more problems on Monday. The concept of equivalent system. Make sure you have a good weekend.